Assalamu alaikum students. Today our topic of discussion is physics of gas diffusion and gas partial pressures. So this is the third chapter from respiration from Guyton. So now we will move towards Guyton. You can see here. Firstly, this is the chapter. So this is the chapter number 39, physical principles of gas exchange, diffusion of oxygen and carbon dioxide through the respiratory membrane. So in the start, after the alveoli are ventilated with fresh air, the next step in the respiratory process is diffusion of oxygen from the alveoli into the pulmonary blood and diffusion of carbon dioxide in the opposite direction out of the blood. So the vice versa movement of oxygen and carbon dioxide occurs. And this process of diffusion is simply the random motion of molecules intertwining their way in all directions through the respiratory membrane and adjacent fluid. So there is random movement. As you know, in diffusion there is random movement. And the physics of gas diffusion and gas partial pressure. First of all, the molecular basis of gas diffusion. So you know that for diffusion, the energy, the source of energy comes from kinetic motion of molecules. So when the molecules strike with each other, they produce kinetic motion of energy. So this energy can be used for diffusion of molecules. And you also know the concept, what is the effect of a concentration gradient on diffusion. The diffusion occurs from high concentration area towards the low concentration area. So it is the main concept of diffusion, as you have already studied in the fourth chapter of Guyton before nerve and muscle. And the other concept regarding diffusion, firstly the concentration gradient, and the second is partial pressure. So you can see here that the pressure is directly proportional to concentration of the gas molecules. So the more the amount of gas molecules, the more is the pressure. And you also know that there are oxygen, nitrogen, carbon dioxide is present in the air. These are the gases, and all of have their own respective partial pressure. And for example, you know that the composition of air, it includes 79% nitrogen and 21% oxygen. So at a sea level, the pressure is 760 millimeter of mercury, and out of 760 millimeter of mercury, 79% is contributed by nitrogen and 21% is contributed by oxygen because of their percentage. So 600 millimeter of mercury is contributed by nitrogen, which is 79% of 760 millimeter of mercury, and the contribution of oxygen is 160 millimeter of mercury. That is 21% of 760 millimeter of mercury. So 600 plus 160 is equal to 760, and you can label the partial pressures of oxygen, carbon dioxide, nitrogen, water, helium, and so forth like this. So Then is the concept of your solubility coefficient. The factors that determine the partial pressure of gas dissolved in a fluid. The partial pressure of a gas in a solution is determined not only by its concentration but also by solubility coefficient. You can see here the Henry law, which states that partial pressure is equal to concentration of dissolved gas over solubility coefficient. So you can see here the concentration of dissolved air is directly proportional to partial pressure, and solubility coefficient is inversely proportional to partial pressure. And you can see here, when the partial pressure is expressed in atmosphere, one atmosphere pressure equals 760 millimeter of mercury, and concentration is expressed in volume of gas dissolved in each volume of water. The solubility coefficient for important respiratory gases at body temperature are the following. So you can see here the solubility coefficient of oxygen and carbon dioxide. You can compare both of these. The solubility coefficient of carbon dioxide is far more than oxygen, about 20 times more. You can see here carbon dioxide is more than 20 times as soluble as oxygen. So this is very important. You can compare the solubility coefficient of oxygen and carbon dioxide. Now you can see here diffusion of gases between the gas phase in the alveoli and the dissolved phase in the pulmonary blood. The partial pressure of each gas in the alveolar respiratory gas mixture tend to force molecules that the gas into the solution into the blood of the alveolar capillaries. So the gas in the alveoli move towards the alveolar capillaries. Conversely, the molecules of same gas that are already dissolved in the blood are bouncing randomly in the fluid of the blood, and some of these bouncing molecules escape back into the alveoli. The rate at which they escape is directly proportional to their partial pressure. So this is the concept. So the effects of oxygen and carbon dioxide are vice versa, because if the partial pressure is greater in the gas phase in the alveoli and is normally true for oxygen, then more molecules will diffuse into the blood than in other direction. Alternatively, if the partial pressure of gas is greater in the dissolved state in the blood, which is normally true for carbon dioxide, then the net diffusion will occur towards the gas phase of the alveoli. So the carbon dioxide moves towards the gas phase of the alveoli, while the oxygen moves towards towards the blood. So what about the vapor pressure of water? When non-humidified air is breathed into the respiratory passageways, water immediately evaporates from the surface of these passages and humidifies the air. So when non-humidified air is breathed, water evaporates. And what is the importance of this evaporation of water? This results from the fact that the water molecules, like the different dissolved gas molecules, are continually escaping from the water surface into the gas phase. The partial pressure that the water molecule exerts to escape through the surface is called vapor pressure of the water. So the pressure by which the water molecules escape is called vapor pressure of the water, which is normally 47 millimeter of mercury at 37 degree centigrade, which is the normal body temperature. And the vapor pressure is entirely dependent on the temperature. As the temperature becomes more, there is more kinetic activity of the molecules, and it leads to more vapor pressure. For example, at 0 degree, the vapor pressure is 5 millimeter of mercury, while at 100 degrees C, the vapor pressure is 760 millimeter of mercury. But you should remember 47 millimeter mercury vapor pressure at body temperature, that is 37 degrees C. So then quantifying the net rate of diffusion in the fluid, in addition to the pressure difference, several other factors affect the rate of gas diffusion in a fluid. They are solubility of a gas in the fluid, the cross-sectional area of the fluid, the distance through which the gas must diffuse, and the molecular weight of the gas, and the temperature of the fluid. So these can be submitted in this equation. You can see here the diffusion is equal to the partial pressure difference, and then A is for the cross-sectional area, and S is the solubility, and D is the distance of diffusion, and MW is the molecular weight. So you can see here the relationship of all these factors with the diffusion, and then is the diffusion coefficients. Regarding diffusion coefficients, you can see here the diffusion coefficient for oxygen is 1, while carbon dioxide has a diffusion coefficient of 20.3, which shows that the carbon dioxide has a diffusion rate of 20 times more than that of oxygen. So these are the few basics of diffusion of gases through the respiratory membrane. And we will now continue with the composition of alveolar air, its relation to atmospheric air, in the next lecture.